We are going to learn about modified Mohr. Now, this theory was developed by Burton Paul in 1961. He was a mathematician, mechanist, and professor and chair of the founding chair of mechanical engineering at the University of Pennsylvania. His theory expands upon the fourth quadrant of the brittle Coulomb-Mohr theory and adjusts the lines within that quadrant to better match experimental data. Now let's look through how this function arises. Case one, let's assume that our principal stresses are both greater than zero, or that the first principal is greater than zero, the second one is less than zero, and the ratio between the second and the first is less than or equal to 1. That is our first case, which produces a line, a vertical line, right? Case 2 is the modification of our fourth quadrant. Here, this is assuming the first principal is greater than 0, and the second principal is less than 0, where the ratio of those two values is greater than 1. In that case, we get a mixed linear equation where we have our compressive minus our tensile strength times sigma A divided by the compressive times the tensile minus sigma B over the compressive is equal to 1 over N, where N is our design safety factor. Now, this equation here is an adjustment of that fourth quadrant in brittle Coulomb-Mohr. Then our last case, case 3, is exactly the same as brittle Coulomb-Mohr. If both of the principal stresses are less than 0, we get a horizontal line where, again, N is our design safety factor. Now, if we plot these three cases and then we apply symmetry to it, we get the failure surface for modified Mohr, where in the first case we have this red line that when when things are positive, we're here, and then when the sigma B is negative, up until the ratio between them is 1, we have this vertical line. At that point, we then have this modification, this mixed case 2, which fits closely to the data, and then we have our third case, this horizontal line, right? Now, if we compare the modified Mohr, this new line, with the previous one we just learned, which is brittle Coulomb-Mohr, which are the gray lines here, we can see that it is slightly less conservative than brittle Coulomb-Mohr. It is closer to the experimental data, meaning that if we were to try to predict failure, our prediction of failure is going to be closer to when our material actually fails, right? Now, there's still a bit of conservatism, so this equation still gives us a little bit of extra safety, but it's not so conservative that this isn't a great theory for us to use, to just go ahead and directly use for a brittle problem with tensile compressive asymmetry. Now, there do exist other more complex failure theories, like nonlinear theories, that are better able to match this experimental data, but their complexity simply is not worth the effort. So if we do have a material with tensile compressive asymmetry, and we don't need a whole lot of safety, we want a little bit more accuracy, modified Mohr is a great theory.